Did you know there's a place in the universe where it rains glass sideways? Or that a single teaspoon of a neutron star weighs as much as a mountain? Space isn't just vast, it's teeming with secrets so bizarre, they defy everything we think we know. And today, we're peeling back the curtain on 30 of the most jaw-dropping, spine-tingling facts about the cosmos that will leave you questioning reality itself. Picture this, floating in the silent blackness of space, where temperatures swing from blistering heat to absolute zero in an instant, where stars explode in colors we can't even name, and where entire galaxies spin like cosmic whirlpools millions of light years wide. It's a realm where the rules of physics twist into knots, where time stretches and warps, and where mysteries lurk in every shadow. Some of these secrets have been hiding in plain sight, while others are so strange even scientists struggle to explain them. But here's the thing, you don't need a telescope or a degree in astrophysics to be stunned by what's out there. Whether you're a casual stargazer or someone who's always dreamed of touching the stars, these facts will rewrite what you thought was possible. From planets made of diamond to black holes that sing, from invisible oceans lurking in the darkness to the eerie hum of the universe itself, each revelation is a piece of a puzzle we're only beginning to solve. So buckle up, by the time we're done, you'll never look at the night sky the same way again. Right now, as you read this, the moon is inching away from us, not at some dramatic, cinematic speed, but slowly, steadily, like a shy dance partner pulling back. Every single year, the moon drifts about 3.8 centimeters farther into the cosmos. That's roughly the width of your thumb. It might not sound like much, but over millions of years, that tiny shift rewrites Earth's very destiny. So why is it happening? Blame the tides. The moon's gravity tugs at our oceans, creating the rise and fall we see on coastlines. But here's the twist. Earth's rotation is actually faster than the moon's orbit, so our planet's spin drags those tidal bulges slightly ahead of the moon. Those bulges, in turn, pull the moon forward like an invisible leash, giving it a tiny boost of energy. And just like a ball on a string, that extra energy pushes the moon into a higher, slower orbit farther from Earth. Now imagine this playing out over eons. In 100 million years, the moon will appear noticeably smaller in our sky. Nights will grow darker, tides weaker. But the real shocker, Earth's days will stretch longer. The same tidal forces slowing the moon also act like a brake on our planet's rotation. Right now, a day lasts 24 hours, but back when dinosaurs roamed, it was closer to 23. In another 50 million years, a day might creep past 25 hours, and the consequences ripple even further. Our climate, seasons, even ocean currents are all shaped by the moon's presence. Without its steadying influence, Earth's axial tilt, the reason we have stable seasons, could wobble chaotically over time, turning our planet into a world of extreme, unpredictable weather. It's a reminder that even the quietest forces in space can rewrite the story of life itself. While we're talking about cosmic oddities, here's one that might make you do a double take. Floating near the center of our Milky Way, there's a cloud so vast it could fuel every pub on Earth for billions of years. Meet Sagittarius B2, a colossal molecular cloud packed with billions upon billions of liters of ethyl alcohol, yes, the same kind you'd find in your favorite drink. This interstellar cocktail party isn't some fleeting phenomenon either. Sagittarius B2 spans over 400 light-years across, swirling with complex molecules like vinyl alcohol and methanol alongside its star ingredient. So how does alcohol, or any molecule for that matter, form in the freezing, airless void of space? It all starts with the remnants of dead stars. When massive stars explode, they scatter elements like carbon, hydrogen, and oxygen into the cosmos. Over eons, these atoms cling to specks of interstellar dust, colliding and bonding in the frigid darkness until voila, entire clouds of organic molecules take shape. But here's the kicker. While the sheer volume of alcohol out there is staggering, you wouldn't want to take a sip. Space-brewed ethanol is laced with toxic compounds like cyanide, and the temperatures hover just above absolute zero. Plus, the cloud's location, 26,000 light-years from Earth, near the supermassive black hole at our galaxy's heart, makes it about as hospitable as a dive bar on the surface of the Sun. What makes Sagittarius B2 truly fascinating, though, isn't just its intoxicating contents. It's a cosmic chemistry lab, proving that the building blocks of life, alcohols, sugars, even amino acids, can form spontaneously in the depths of space. Some scientists speculate that clouds like these could have seeded young planets with the organic ingredients needed for life to emerge. So next time you raise a glass, remember, the universe might have been mixing drinks long before we were. If you think Earth's hurricanes are terrifying, Venus takes extreme weather to a whole new level. On this scorching, toxic world, winds scream across the landscape at 724 kilometers per hour, nearly 2.5 times faster than the most powerful tornado ever recorded on Earth. But here's what makes these supersonic gusts truly mind-bending. They're moving faster than the planet itself rotates. That's right, Venus's atmosphere is in such a frenzy. It outruns the planet's own sluggish spin, a phenomenon scientists call superrotation. Picture a world where the air itself is in revolt. While Venus takes 243 Earth days to complete a single rotation, its day longer than its year, its atmosphere completes a full lap around the planet in just 4 Earth days. It's like a marathon runner lapping a snail. So what's fueling this atmospheric rebellion? The culprits are Venus's thick, suffocating blanket of carbon dioxide and its runaway greenhouse effect. Sunlight heats the planet's surface to a blistering 460 degrees Celsius, enough to melt lead. That heat gets trapped under dense clouds of sulfuric acid, creating extreme temperature differences between the day and night sides. These imbalances trigger monstrous winds that race from the scorching equator toward the slightly cooler poles, gaining speed as they go. But the weirdness doesn't stop there. Unlike Earth's winds, which are chaotic and turbulent, Venus's supersonic flow is eerily smooth, more like a single, planet-sized river of air. Probes like the European Space Agency's Venus Express have even detected giant hurricane-like vortices swirling at both poles, each large enough to swallow continents whole. What's baffling is how this system sustains itself. With no oceans or mountains to disrupt the flow, Venus's winds just keep accelerating, dragging the entire atmosphere along like a cosmic conveyor belt. Some researchers think atmospheric tides caused by the Sun's gravitational pull on Venus's thick air might be adding energy to the mix, while others suspect mysterious waves in the atmosphere are transferring momentum. One thing's certain, if you ever found yourself on Venus, you wouldn't just be crushed by the pressure or boiled alive. You'd be hurled across the landscape faster than a bullet, wrapped in a never-ending storm of superheated poison. It's a stark reminder that even in our own solar system, nature can cook up weather so extreme it defies imagination. Now let's take a trip to Mercury, the speedster of the solar system, except when it comes to its days. This tiny, cratered world has a routine so bizarre, it flips our earthly expectations upside down. On Mercury, a single day, the time from one sunrise to the next, lasts a staggering 176 Earth days. But here's the twist. The planet whips around the sun so fast, its entire year is over in just 88 Earth days. That means if you lived on Mercury, you'd celebrate 2 birthdays before the sun even finished crossing the sky once. So how does this cosmic contradiction happen? It all comes down to a gravitational tug of war between the sun's overwhelming pull and Mercury's oddball rotation. Most planets spin at a steady pace while they orbit, but Mercury's rotation is locked in a strange dance called a 3-2 spin orbit resonance. For every 2 trips it makes around the sun, it spins exactly 3 times on its axis. This sluggish spin, combined with its breakneck orbital speed racing at nearly 170,000 kilometers per hour, creates that jaw-dropping mismatch between days and years. Imagine standing on Mercury's surface. The sun wouldn't move smoothly across the sky like it does here. Instead, it would rise, pause, reverse course like it's second-guessing itself, then finally barrel forward again. At certain points near Mercury's poles, you could even watch the sun dip below the horizon, change its mind, and climb back up before finally setting hours later. It's like the universe itself glitched. The consequences of this odd rhythm are just as extreme. With such long days, the side facing the sun bakes at temperatures hot enough to melt lead, while the night side plunges to near absolute zero. There's no atmosphere to distribute the heat, so the temperature swings are some of the most violent in the solar system. And yet, despite these extremes, shadows on Mercury hold a chilling secret: permanently dark craters at its poles where sunlight hasn't reached in billions of years, possibly hiding vast deposits of ice in the unlikeliest of places. Mercury's chaotic calendar is a reminder that even the simplest assumptions about time and space can shatter when you step beyond Earth. It's not just a world of extremes, it's a cosmic riddle, spinning and orbiting in ways that still leave scientists scratching their heads. In the cosmic menagerie of bizarre objects, neutron stars are in a league of their own. Imagine taking the entire mass of our sun and crushing it down into a sphere the size of Manhattan. That's the sheer, incomprehensible density of a neutron star. But here's the real showstopper. Some of these stellar remnants spin so fast, they complete 600 full rotations every single second. That's not a typo. At that speed, the surface of the star is whipping around at nearly 1/5 the speed of light, distorting space-time itself like a cosmic blender. So how does something so massive spin that fast without tearing itself apart? It all starts with a violent death. When a massive star runs out of fuel, it doesn't fade quietly, it collapses in a supernova explosion so powerful, it outshines entire galaxies for weeks. What's left behind is a city-sized core so dense, a single sugar cube of its material would weigh as much as Mount Everest. But here's the kicker. Just like an ice skater pulling their arms in to spin faster, the collapsing star's core speeds up dramatically as it shrinks. Conservation of angular momentum means what was once a leisurely stellar rotation, say, once every few weeks becomes a dizzying, milliseconds-long whirl. And the effects of that spin are downright surreal. The rapid rotation creates intense magnetic fields billions of times stronger than Earth's, launching beams of radiation from the star's poles. If these beams happen to sweep past Earth, we detect them as precise, rapid-fire pulses of light, earning these stars the nickname pulsars. Some pulsars are so regular, their ticks are more reliable than atomic clocks. But the real jaw-dropper, the fastest known neutron star, named PSRJ 1748-2446 AD, spins 716 times per second. At that rate, if you stood on its surface, ignoring the fact that you'd be instantly flattened into a pancake, you'd experience centrifugal forces so strong they'd hurl you into orbit before you could blink. Yet even these cosmic speed demons slow down over time, their furious spins gradually braked by their own magnetic fields and the energy they radiate into space. Some eventually become so sluggish they rotate just a few times per minute. But for now, neutron stars remain the universe's ultimate spinning tops, reminders that when nature collapses matter to its limits, the results are anything but ordinary. Here's something that might unsettle you. The vast, star-filled expanse of space is utterly, absolutely silent. No whooshing starships, no roaring explosions, not even the faintest whisper of wind, just an endless, suffocating quiet. While Hollywood loves to pump sci-fi battles with dramatic sound effects, the reality is far eerier. In space, no one can hear you scream, and it's not just a tagline, it's physics. Sound, as we know it, needs a medium to travel through, like air, water, or even solid ground. but space is a near-perfect vacuum with atoms so sparse they might as well not exist. Without molecules to bump into each other and carry vibrations, sound waves simply can't propagate. That means even the most cataclysmic events, supernovas tearing apart stars, black holes shredding planets, galaxies colliding, happen in complete silence. So how do astronauts communicate? Radio waves. Unlike sound, these electromagnetic waves don't need air to travel. They zip effortlessly through the void, allowing crews aboard the International Space Station to chat with mission control or even take phone calls from orbit. But here's the catch. Inside their spacecraft or suits, astronauts fill the silence with artificial sound, beeping alarms, humming machinery, the occasional playlist, because the human brain isn't built for total quiet. Studies show prolonged silence can trigger disorientation and even hallucinations, which is why NASA meticulously designs environments with purposeful noise. The silence of space isn't just empty, it's active. That absence of sound shapes everything from spacecraft design to how we explore. Probes like Voyager carry golden records with Earth sounds, not because aliens could hear them in space, but because if they're ever found and brought into an atmosphere, those recordings would finally have a medium to come alive. Meanwhile, telescopes like Hubble don't just see the cosmos. They translate light into data that scientists sometimes sonify, turning distant galactic radiation into eerie, synthetic tones we can perceive. Think about that the next time you look up. The universe isn't just vast and dark, it's mute, a symphony of unimaginable violence playing on the grandest stage with no audience to hear it. And yet, we keep listening. Think about holding a basketball in your hands. Now imagine it outweighing every grain of sand on every beach, every mountain range, and every skyscraper on Earth combined. That's the sheer scale of the Sun's dominance in our solar system. This glowing sphere of superheated plasma accounts for a staggering 99.86% of everything with mass in our cosmic neighborhood. The remaining 0.14%, that's all the planets, moons, asteroids, comets, space dust, and even the occasional wandering meteor. Everything else just crumbs in comparison. To grasp how lopsided this is, picture the solar system as a pie chart. The Sun isn't just the biggest slice, it's the entire pie with a few microscopic specks of dust sprinkled on top. Jupiter, the largest planet, makes up about 2/3 of that minuscule leftover fraction. Saturn, Uranus, and Neptune claim most of the rest, Earth. We're a barely their speck, 1/300,000th of the Sun's mass. You could fit 1.3 million Earths inside the Sun's volume and still have room to spare. But here's what really puts it into perspective. The Sun's gravity is so overwhelming, it doesn't just keep planets in orbit. It bends the very fabric of space-time around it like a bowling ball on a trampoline. Every object in the solar system, from the tiniest pebble in the asteroid belt to the icy giants at the edge of the Kuiper belt, dances to the Sun's tune. Even the Voyager probes, now hurtling through interstellar space, are still technically under the Sun's gravitational influence, though they've left its magnetic bubble behind. What's wild is how ordinary this arrangement is. Most star systems follow the same blueprint. A single, massive star calling the shots with planets as afterthoughts. Yet without this imbalance, life as we know it wouldn't exist. The Sun's crushing gravity forces its core to reach temperatures of 15 million degrees Celsius, igniting the nuclear fusion that bathes our planet in light and warmth. It's the ultimate cosmic trade-off, a star so massive it dictates the rules, but so precise in its power that it nurtures the delicate conditions we call home. So next time you feel small under that bright midday sky, remember, you're standing in the presence of a titan that holds the entire solar system in its grasp, and we're all just along for the ride. Deep in the constellation Cancer, 40 light-years from Earth, there's a world that would make even the most extravagant jewelers blush. Meet 55 Cancri E, a planet twice the size of our own, but here's where the ordinary ends. Scientists believe this super-Earth isn't made of rock or iron like our home, but something far more dazzling. Layers of graphite and diamond so thick they could outweigh all the gems ever mined on Earth combined. How does a planet become a cosmic treasure chest? It starts with its star. 55 Cancri, the planet's sun, is unusually rich in carbon, the same element that forms diamonds under extreme pressure. When this system was born, that carbon didn't just stay in the star. It clumped together in the surrounding disk, forming planets with chemistry unlike anything in our solar system. Picture a world where the very ground beneath your feet isn't silicate rock, but compressed carbon crystals. The planet's surface might resemble a dark graphite landscape, but dig just 100 kilometers down, a stone's throw in planetary terms, and you'd hit a layer of diamond hundreds of miles thick, forged by pressures 1,000,000 times greater than Earth's atmosphere. But don't pack your mining gear just yet. 55 Cancri E orbits so close to its star, a year lasts just 18 hours. Daytime temperatures soar above 2,000 degrees Celsius, hot enough to vaporize steel and turn diamonds into puddles of liquid carbon. And that's if the planet even has a surface. Some models suggest it might be so molten. The entire world is one churning ocean of superheated diamond sludge, with icebergs of solid gemstone floating atop seas of carbon lava. The real kicker, this isn't the only diamond planet out there. In 2013, astronomers spotted another candidate near the center of our galaxy, the remnant core of a dead star compressed into a crystalline sphere. But 55 Cancri E is special. It's the first we've found that's not just a diamond in the rough, but a gleaming testament to how alien planetary chemistry can truly get. What's fascinating isn't just the bling factor. Planets like this force us to rethink how worlds form. Our solar system, built around a silicon-rich sun, sprouted rocky planets and gas giants. But around carbon-heavy stars, the cosmic recipe might bake worlds of tar, graphite, and diamond, places where mountains could literally be made of gemstones and rivers could flow with liquid hydrocarbons. It's a reminder that the universe doesn't just deal in extremes, it reinvents them. For centuries, Jupiter's Great Red Spot has been the solar system's most mesmerizing storm, a swirling crimson maelstrom wider than Earth itself, raging with winds that top 640 kilometers per hour. But this iconic tempest, a fixture in Jupiter's clouds since at least the 1600s, is quietly vanishing before our eyes. Measurements show the storm has been shrinking for over 150 years, and today, it's less than half the size it was when astronomers first trained their telescopes on it. The numbers tell a sobering story. In the late 1800s, the Great Red Spot stretched 40,000 kilometers across, wide enough to fit 3 Earths side by side. By the time Voyager flew past in 1979, it had dwindled to 23,000 kilometers. Now, it's barely 16,000 kilometers wide and shrinking by about 900 kilometers per year. At this rate, some models predict it could fade into a memory within our lifetimes. So what's stealing Jupiter's signature storm? The answer lies in the chaos of the planet's atmosphere. Unlike Earth's hurricanes, which feed off warm ocean water and fizzle out over land, the Great Red Spot is a high-pressure anticyclone, powered by Jupiter's furious internal heat and the collision of opposing jet streams. But as these streams weaken or shift, possibly due to changes in Jupiter's deep weather layers, the storm loses its energy source. Smaller vortices, like swirling white ovals, now nibble at its edges, stealing momentum and accelerating its decline. Yet the storm isn't going down without a fight. Recent observations reveal it's growing taller as it shrinks sideways, stretching vertically like taffy. Some scientists think this could be its last gasp, a desperate attempt to conserve energy by trading width for height. Others speculate it might stabilize, becoming a smaller but more intense remnant of its former self. What's truly humbling is the scale of time here. This storm has likely roared for centuries, outlasting empires and civilizations. Its slow fade reminds us that even the mightiest phenomena in the cosmos are temporary, and that we're witnessing in real time the end of a celestial era. The coldest place in the universe isn't some frozen wasteland at the edge of a distant galaxy. It's right here on Earth in a lab. While space itself chills at around -270 degrees Celsius, thanks to the faint glow of the Big Bang's leftover radiation, scientists have shattered that record in controlled experiments. Using lasers and magnetic fields, researchers have manipulated atoms to reach temperatures just a hair above absolute zero, the theoretical point where all motion stops. We're talking -273.15 degrees Celsius, a fraction of a degree from the coldest possible temperature in existence. But how does a lab on Earth out-freeze the vast emptiness of space? The secret lies in the Boomerang Nebula, a cosmic oddity 3,000 light-years away. This dying star's expanding gas cloud acts like a cosmic refrigerator, dropping temperatures to -272 degrees Celsius, 1 degree warmer than absolute zero. That's colder than the natural background of space itself, making it the universe's natural record holder. Yet here's the catch: while the nebula's chill is mind-boggling, it's still no match for human ingenuity. In labs like MIT and the University of Bremen, physicists use Bose-Einstein condensates, a state of matter where atoms move in eerie unison, to push the boundaries of cold. By trapping atoms with lasers and then slowly bleeding away their energy, they create conditions so frigid, quantum effects become visible to the naked eye. Atoms stop behaving like particles and instead act like waves, overlapping and merging in ways that defy classical physics. What's wild is why we bother. These experiments aren't just about breaking records, they're windows into the quantum realm, helping us understand superconductivity, dark energy, and even the fabric of space-time. The coldest spots in the universe, both natural and man-made, remind us that temperature isn't just about numbers. It's a frontier where the rules of reality bend, and where a fraction of a degree can unlock secrets hidden since the dawn of time. The sheer density of a neutron star defies all earthly intuition, so much so that a single teaspoon of its material would tip the scales at a staggering 1 billion tons. To grasp that absurdity, picture squeezing Mount Everest into a sugar cube. That's the level of cosmic compression we're talking about. When a massive star exhausts its fuel and collapses under its own gravity, the resulting supernova doesn't just leave behind a dense core, it forges a remnant so compact even atoms can't hold their structure. Protons and electrons are crushed together into neutrons, packing the mass of 1.4 suns into a sphere no wider than a city. What does that density feel like? Imagine holding that teaspoon of neutron star material in your palm. On Earth, its weight would create a gravitational pull so intense, it would instantly bore through the planet's crust like a bullet through tissue paper, sinking toward the core. The only thing preventing this in space is the star's own gravity, which balances the mind-bending pressure. But here's the twist: neutron stars aren't just dense, they're flawless. Their surfaces are so smooth, any mountains, wrinkles in the crust would measure mere millimeters tall. A single imperfection over 5 millimeters would trigger starquakes, releasing energy equivalent to a magnitude 32 earthquake. Yet the real shocker is how these stars warp the very fabric of reality around them. Their gravitational pull is so intense, light emitted from their surface reddens dramatically as it fights to escape a phenomenon called gravitational redshift. If you stood on the surface and somehow survived the tidal forces that would spaghettify your body, you'd see the universe distorted into a narrow band of light above you, like looking up from the bottom of a bottomless well. Neutron stars are cosmic overachievers, pushing matter to its absolute limit. They're reminders that the universe doesn't just bend the rules, it obliterates them, crafting objects so extreme they redefine what we thought was possible. We often hear that the universe is vast, but the numbers behind its scale are almost impossible to comprehend. Consider this: If you took every single grain of sand from every beach, every desert, and every seabed on Earth, the total would pale in comparison to the number of stars glittering in the cosmos. Scientists estimate our Milky Way alone houses roughly 100 billion stars, but that's just our galactic neighborhood. Peer deeper, and the count spirals into mind-numbing territory. The latest astronomical surveys suggest there are at least 2 trillion galaxies in the observable universe, each brimming with hundreds of billions of stars. Do the math and you're staring at a figure so colossal it defies human intuition. Roughly 10,000 stars for every grain of sand on our planet. To put that in perspective, scoop up a handful of sand from your favorite beach. Those few thousand granules in your palm would represent millions of stars scattered across the void. But here's what makes this even wilder. Those 2 trillion galaxies are just what we can see. The observable universe stretches 93 billion light-years in diameter, limited by the distance light has had time to travel since the Big Bang. Beyond that, the true extent of the cosmos could be infinite, meaning the actual number of stars might be uncountable. Some theories suggest there could be more stars in the universe than atoms in the entire observable part of it, an idea so dizzying it borders on philosophical. And yet, despite this unimaginable abundance, the night sky looks deceptively quiet to our eyes. Light pollution and the limitations of human vision mean we only see about 2,500 stars on the clearest night. The rest, those countless trillions, remain hidden, their light too faint or too distant to reach us. Telescopes like Hubble and James Webb have peeled back the curtain, revealing galaxies so far away, their light has traveled for over 13 billion years to reach us. This staggering scale isn't just a fun fact, it reshapes how we understand our place in the universe. Every star we see is a potential sun, likely orbited by planets, some of which may harbor life. With numbers this vast, the odds tilt dramatically in favor of Earth not being special, but simply one among countless other worlds. It's a humbling thought. We're not just living on a pale blue dot. We're floating in an ocean of stars so vast it makes even the grandest deserts look like a single speck of dust. When you gaze at a starry sky, you're not just seeing distant points of light, you're looking back in time. That twinkle from Sirius, it left that star 8 years ago. The glow of Andromeda, 2.5 million years in the past, but the Hubble Space Telescope takes this cosmic time travel to another level entirely. Its most famous images, like the Hubble Deep Field, don't just capture faraway galaxies, they freeze moments from when the universe was a fraction of its current age, turning the telescope into a time machine with a lens. Here's how it works. Light doesn't travel instantly. Even at 300,000 kilometers per second, crossing the cosmos takes eons. When Hubble peers into what looks like empty space, it's collecting photons that have been racing toward us for billions of years. The deep field image, for instance, a tiny patch of sky no larger than a grain of sand held at arm's length, reveals over 3,000 galaxies, some so ancient their light predates Earth itself. We're seeing them not as they are today, but as they were when the universe was just 5% of its current age. But Hubble's time-bending power goes deeper. Some of the faintest smudges in its images are galaxies so remote, their light has been stretched by the expansion of the universe into infrared wavelengths invisible to our eyes. This redshift effect is like cosmic Doppler shift, the same phenomenon that makes a siren's pitch drop as it moves away, but applied to starlight. By measuring this shift, astronomers can calculate exactly how long that light has been traveling. What's staggering is the precision of these snapshots. Hubble doesn't just show us that the early universe existed, it reveals how it looked. Galaxies from 13 billion years ago aren't the elegant spirals we know today. They're chaotic, misshapen blobs, colliding and merging in the turbulent youth of the cosmos. These images confirm theories about galaxy formation while throwing curveballs, like the discovery of mature galaxies that appear too old for their cosmic era, forcing scientists to rethink timelines. And the implications ripple beyond astronomy. Every photon Hubble captures is a data point in the story of existence itself. The telescope has glimpsed the epoch of reionization, when the first stars burned away the cosmic fog and spotted quasars so bright they outshine galaxies fueled by black holes that shouldn't have existed so soon after the Big Bang. Each observation is a puzzle piece in answering humanity's oldest questions. Where did we come from? How did everything begin? The irony is delicious. A machine orbiting Earth built by human hands can peer back to moments before planets, even before atoms fully formed. It's a reminder that the night sky isn't just a place. It's an archive, and Hubble is the ultimate historian, translating faint light into chapters of the universe's biography we're only beginning to read. Mars holds a record that makes even Earth's mightiest mountains look like foothills. Olympus Mons, a volcano so massive, it redefines the word colossal. Towering 22 kilometers above the Martian surface, this shield volcano isn't just taller than Mount Everest, it dwarfs it by a factor of 3. But the height is only half the story. Olympus Mons stretches 600 kilometers across at its base, roughly the size of the entire state of Arizona. If you stood at its peak, the slope would be so gradual you wouldn't even realize you were climbing. The horizon would curve away from you, lost in the planet's thin, dusty haze. How does a volcano grow to such mind-bending proportions? Blame Mars's lack of plate tectonics. On Earth, shifting continental plates limit how long a volcano can stay active in one spot. But Mars's crust is static, allowing magma to erupt from the same vent for billions of years, piling layer upon layer of lava into a single gargantuan peak. Picture a fountain of molten rock erupting non-stop for ages, not in violent explosions, but in slow, syrupy flows that spread outward like pancake batter on a griddle. Over eons, these flows built Olympus Mons into the solar system's ultimate skyscraper, and the features don't stop at size. The summit caldera, a hollow, bowl-shaped depression, spans 80 kilometers, large enough to swallow entire cities. Cliff-like scarps ring the volcano's base, some towering 7 kilometers high, where lava once met resistance and piled up like frozen tidal waves. Yet despite its enormity, Olympus Mons is shockingly young by geological standards. Some lava flows on its flanks may be as recent as 2 million years old, hinting that the volcano might not be entirely dead, just napping. What's truly wild is imagining the view from the top. Mars's thin atmosphere means you'd see the stars even at midday, while the volcano's own bulk would block half the planet from sight, and if you tripped, you'd take a full minute to fall, not because gravity is weaker, but because the slopes are so gentle you'd barely roll. Olympus Mons isn't just a geological oddity. It's a monument to how differently planets evolve when freed from Earth's restless, shifting crust. A mountain so vast it doesn't just rise above the landscape, it dominates an entire world. Saturn's dazzling rings, the crown jewels of our solar system, are performing a slow-motion vanishing act. Those iconic bands of ice and rock, stretching over 280,000 kilometers wide but barely thicker than a skyscraper is tall, are being steadily devoured by the planet's gravity. Every second, an Olympic swimming pool's worth of ring material rains down onto Saturn's upper atmosphere in a shimmering, doomed waterfall of cosmic debris. At this rate, astronomers estimate the rings could be gone in as little as 100 million years, a blink of an eye in planetary time. What's pulling them apart? A deadly combination of gravity, sunlight, and magnetic forces. Saturn's immense gravity tugs at the icy particles, while ultraviolet light from the sun charges them, making them vulnerable to the planet's magnetic field. These charged particles then spiral along magnetic field lines, dragging them toward Saturn's poles in glowing streams. The Cassini spacecraft caught this process in action during its final orbits, detecting complex organic molecules, the building blocks of life, raining down with the ring material. It's as if Saturn is not just destroying its rings, but repurposing them into ingredients for something new. The irony is that these rings might already be living on borrowed time. Evidence suggests they're a relatively recent addition to Saturn, possibly forming just 100 million years ago, around the time dinosaurs ruled Earth. That means we're witnessing a fleeting cosmic spectacle, a temporary adornment that future civilizations might never see. Some theories even propose the rings are the shattered remains of a moon that wandered too close and was torn apart by tidal forces, making their eventual fate a poetic full circle. Yet the real mystery isn't just their disappearance, it's the staggering speed of it. Earlier estimates suggested the rings could last another billion years, but new data from Cassini revealed they're losing mass up to 100 times faster than previously thought. This means the rings we see today are already shadows of their former selves, their particles steadily eroding like sand slipping through an hourglass. What's left behind when they're gone? A subtle, permanent mark. The infalling material alters Saturn's upper atmosphere, leaving traces of water and complex chemistry in its wake. Future telescopes might detect these ghostly fingerprints, the only clue that a ring system once orbited where now there's only empty space. It's a humbling reminder. Even the most breathtaking features in our universe are often just passing wonders, here for a cosmic moment before fading into the dark. Even in the deepest voids between galaxies, space isn't truly cold, not by cosmic standards. The universe hums with a faint, uniform warmth, a thermal whisper left over from its explosive birth. This residual heat, known as the cosmic microwave background radiation, blankets all of existence at a crisp 2.7 degrees above absolute zero. It's the oldest light we can detect, stretching back to when the cosmos was just 380,000 years old, a time when the universe cooled enough for atoms to form, releasing photons that have been traveling ever since. Picture the aftermath of a fireworks display when the air still crackles with warmth and the scent of sulfur. The cosmic microwave background is like that, but on a scale so vast it permeates every cubic centimeter of space. Discovered by accident in 1964 by astronomers Arno Penzias and Robert Wilson, this ghostly glow was initially mistaken for pigeon droppings interfering with their radio antenna. But the signal persisted, a steady hiss coming from every direction, unchanging whether they pointed their equipment at the center of the Milky Way or the emptiest patch of sky. What makes this radiation so remarkable isn't just its ubiquity, but its near-perfect uniformity. Across the entire observable universe, the temperature varies by less than 100,000th of a degree. These tiny fluctuations, mapped in exquisite detail by satellites like COBE and Planck, are the fingerprints of the early cosmos regions where matter was ever so slightly denser, eventually seeding the galaxies and superclusters we see today. Without those minuscule variations, gravity would have had nothing to grab onto, leaving the universe a featureless soup of hydrogen and helium. Yet the cosmic microwave background isn't just a relic, it's still shaping our understanding of physics. Its patterns hint at the universe's composition: 5% ordinary matter, 27% dark matter, and 68% dark energy. It's also the ultimate time capsule, preserving echoes of quantum fluctuations from the first trillionth of a second after the Big Bang, when the entire cosmos was smaller than a single atom. So next time you feel a chill on a winter night, remember, even the coldest, darkest stretches of space are bathed in the faint afterglow of creation. A reminder that the universe hasn't just expanded, it's still cooling from the firestorm that birthed it. Imagine all the water on Earth, every ocean, lake, and raindrop multiplied by 140 trillion. Now picture that unimaginable volume floating in space, not as liquid, but as vapor swirling around a brilliant quasar 12 billion light-years away. This isn't science fiction, it's the staggering reality of APM 08279 plus 5255, a cosmic mirage harboring the largest reservoir of water ever detected. Quasars are the universe's ultimate powerhouses, supermassive black holes devouring matter so furiously they outshine entire galaxies. But this particular quasar hides a surprise. In 2011, astronomers using the Z-spec instrument at Caltech's Submillimeter Observatory found its light filtered through a cloud of water vapor so vast it defies comprehension. The numbers are dizzying, enough water to fill Earth's oceans 140 trillion times over, or to shower every known planet in the Milky Way with an ocean dozens of miles deep. How does water, something so essential to life, exist in such extreme quantities near a black hole? The secret lies in the quasar's anatomy. As matter spirals toward the black hole, it forms a superheated accretion disk glowing with the energy of a trillion suns. Surrounding this inferno is a torus, a donut-shaped region of gas and dust spanning hundreds of light years. Here, in the cooler outer edges, water molecules form and thrive, energized by the quasar's radiation but shielded from its full destructive force. But here's what makes this discovery truly mind-bending. We're seeing the quasar as it existed 12 billion years ago, just 1.6 billion years after the Big Bang. That means this colossal water cloud existed when the universe was barely a teenager, proving that the ingredients for life, or at least its most vital component, were already abundant in cosmic terms almost immediately after the first stars ignited. The implications ripple far beyond a single quasar. Water, it turns out, is far more common in the universe than we ever suspected. From the ice-covered moons of Jupiter to the frigid molecular clouds between stars, H2O seems to be everywhere. But APM 08279 plus 5255 isn't just another wet spot in space, it's a cosmic flood. A reminder that the universe doesn't just harbor life's potential in rare, special places. It's swimming in it on scales so vast they rewrite our understanding of chemistry, time, and our own humble place in the grand scheme of things. What's more, this vapor cloud isn't static. It's part of a dynamic system where water molecules are constantly forming, breaking apart, and reforming, a cycle that may have seeded future generations of stars and planets with the raw materials for oceans, atmospheres, and perhaps even life itself. So next time you take a sip of water, remember, the universe didn't just give us a few raindrops, it handed us an entire galactic inheritance, forged in the hearts of quasars and scattered across the cosmos like an endless, life-giving mist. Pluto's calendar is unlike anything we experience on Earth. While our planet completes its journey around the Sun every 365 days, Pluto takes a staggering 248 Earth years to finish just one orbit. That means if you were born on Pluto, ignoring the lethal cold and lack of breathable air, you'd celebrate your first birthday around the time the United States was declaring its independence in 1776. Seasons on this distant world aren't measured in months, but in decades-long stretches of twilight where a single summer or winter could outlast a human lifetime. What makes Pluto's orbit so punishingly slow? The answer lies in its eccentric path. Unlike Earth's nearly circular orbit, Pluto follows a stretched-out elliptical route that swings wildly from 30 to 49 astronomical units from the Sun. At its closest approach, it briefly dips inside Neptune's orbit before recoiling to the frozen edges of the solar system. This elongated trajectory, combined with the Sun's weak gravitational pull at such distances, forces Pluto to crawl through its journey at an average speed of just 4.7 kilometers per second, 1/6 the pace of Earth. The consequences of this glacial orbit are surreal. Sunlight on Pluto is so faint it would feel like perpetual dusk even at high noon. But when the dwarf planet nears perihelion, its closest point to the Sun, the weak rays trigger dramatic changes. Frozen nitrogen, methane, and carbon monoxide on its surface sublimate into a thin, temporary atmosphere, creating winds that push exotic snow across glaciers of solid nitrogen. Then, as Pluto retreats, this atmosphere freezes back onto the ground like a celestial exhale turning to frost. Seasons here defy imagination. with an axial tilt of 120 degrees Earth is just 23.5. Pluto essentially rolls on its side as it orbits. This means some regions spend over a century in continuous sunlight, followed by another century of unbroken darkness. The slow creep of these seasons allows ice caps dozens of miles thick to form and vanish over centuries, while bizarre, bladed terrain, made of jagged methane ice towers as tall as skyscrapers, erodes at a pace visible only across generations. Even more fascinating, Pluto's year isn't just long, it's chaotic. Interactions with Neptune and other Kuiper belt objects cause its orbit to wobble unpredictably over millions of years, a phenomenon called orbital resonance. Computer simulations suggest that over cosmic timescales, Pluto's path could become even more elongated or even flip entirely, turning its current trajectory upside down. For spacecraft like New Horizons, which captured stunning images during its 2015 flyby, timing was everything. The probe arrived just as Pluto was beginning its decades-long retreat from the Sun, offering a fleeting glimpse of its active surface before the long freeze set in. By the time Pluto completes another orbit in the year 2173, human civilization may have transformed beyond recognition, but this distant world will still be ticking through its slow, cosmic clock, one frosty season at a time. While we often think of earthquakes as an earthly phenomenon, our moon has its own version: moonquakes, seismic tremors that ripple through the lunar crust with surprising regularity. Unlike Earth's quakes, which are mostly driven by shifting tectonic plates, these lunar shudders come from two far stranger sources: the relentless gravitational tug of war with Earth and the moon's own slow, inexorable cooling. The Apollo astronauts left more than footprints on the lunar surface. They planted seismometers that recorded thousands of these events between 1969 and 1977. The data revealed 4 distinct types of moonquakes, the deepest and most powerful, reaching magnitudes up to 5.5, originate 700 kilometers below the surface, where Earth's gravity stretches and squeezes the moon's interior like a cosmic stress ball. These tidal quakes follow a strict schedule, peaking every 27 days as the moon reaches its closest point to Earth in its elliptical orbit. But the most unsettling tremors come from the moon's shrinking core. As the moon cools over billions of years, its crust contracts, cracking like a drying mudflat. These shallow moonquakes, though less frequent, can last over 10 minutes compared to Earth's quakes that typically end in seconds. The reason: without water or atmosphere to erode and soften the rock, the moon's crust remains brittle, allowing seismic waves to echo endlessly through its rigid structure. Some of these quakes left scars visible from orbit, fresh-looking cliffs called lobate scarps, some as tall as the Eiffel Tower. What's eerie is how differently these tremors behave. On Earth, quakes fade quickly as waves dissipate through our planet's molten layers. But the moon's dry, rigid body rings like a bell, with vibrations sometimes continuing for hours. Apollo seismometers even picked up moonquake echoes, seismic waves that circled the entire moon multiple times before fading. The implications are profound for future lunar bases. While moonquakes aren't as intense as Earth's worst temblors, their duration and the moon's lack of seismic damping mean even a moderate quake could rattle structures relentlessly. Engineers might need to design floating foundations or shock-absorbing materials to withstand these marathon tremors. Yet these quakes aren't just hazards, they're clues. By studying their patterns, scientists have mapped the moon's internal structure, discovering a partially molten core and layers of fractured rock from ancient impacts. Each tremor is like an ultrasound pulse, revealing secrets about our nearest celestial neighbor's turbulent past and its slow, silent transformation into the cold, quaking world we see today. Astronauts returning from spacewalks often report a bizarre scent clinging to their suits, a metallic, almost charred aroma that some describe as a mix of seared steak, hot metal, and welding fumes. This cosmic perfume isn't some phantom smell. It's the lingering residue of the universe itself, clinging to their gear like interstellar campfire smoke. The source of this otherworldly odor lies in the death throes of stars. When massive stars explode as supernovas, they spew complex molecules like polycyclic aromatic hydrocarbons, the same compounds found in burnt toast and car exhaust, into the void. These particles hitch rides on cosmic dust, drifting for eons until they cling to the surfaces of spacesuits during spacewalks. The moment astronauts repressurize the airlock, oxygen interacts with these exotic compounds, triggering chemical reactions that release that distinctive burnt metal tang. But the smell isn't just about dying stars. The International Space Station's own environment plays a role. Materials exposed to the vacuum of space undergo a process called outgassing, where trapped gases and volatile compounds slowly escape from metals, plastics, and even fabrics. When these molecules mingle with the cosmic dust on a suit, they create a cocktail of odors unlike anything on Earth. Russian cosmonauts have likened it to the scent of a smoky barbecue, while NASA astronauts often compare it to the acrid bite of a just extinguished match. What's fascinating is how this scent varies. Some spacewalkers report sharper, almost ozonic notes, likely from atomic oxygen clinging to their suits, a highly reactive form of the element that doesn't exist naturally on Earth's surface. Others detect a faint, gunpowder-like bitterness, possibly from nitrogen compounds formed under the harsh radiation of space. The European Space Agency even conducted experiments to replicate the smell synthetically, using sterile clean rooms and irradiated metals to help train astronauts for the sensory surprises of spaceflight. This phenomenon isn't just a quirky footnote, it's a visceral reminder that space isn't empty. It's a dynamic chemical tapestry where the remnants of stellar explosions brush against human technology, leaving behind traces we can literally smell. Every whiff of that metallic char is a direct encounter with the cosmos, a sensory handshake between humanity and the universe's grand elemental cycles. And there's a poetic irony here. That seared steak aroma, it might share molecular cousins with the very compounds that seeded life on Earth billions of years ago. The same cosmic dust that perfumes astronaut suits could have once rained down on our planet, carrying the raw ingredients for water and organic molecules. So in a way, that strange scent isn't just space, it's the smell of our own ancient origins, lingering in the void like a ghostly breadcrumb trail. Earth doesn't just have one moon, it has a mysterious dance partner that's been hiding in plain sight for centuries. Meet Neutron, a 5-kilometer-wide asteroid that shares our orbit around the Sun in an intricate gravitational ballet. Unlike our familiar lunar companion, Neutron doesn't circle Earth directly. Instead, it follows a horseshoe-shaped path around the Sun that syncs perfectly with our planet's movement, creating the illusion of a second moon chasing us through space. This cosmic tag-along was discovered in 1986, but its true relationship with Earth wasn't understood until a decade later. Neutron takes exactly 1 year to orbit the Sun, matching Earth's annual journey, but it does so on a wobbling, bean-shaped trajectory that alternately leads and trails our planet. Every 385 years, this dance brings Neutron tantalizingly close, just 12 million kilometers away, 30 times farther than the Moon before it swings back out again on its elongated path. What makes Neutron's motion so mesmerizing is its resonance with Earth's gravity. As the asteroid approaches from behind, our planet's pull gives it an energy boost, flinging it into a slightly larger orbit that slows its progress. When Neutron laps us and approaches from ahead, Earth's gravity does the opposite, tugging it backward into a smaller, faster orbit. The result is an endless game of celestial leapfrog where the two bodies never collide, yet never truly part ways. This dynamic makes Neutron a quasi-satellite, not a true moon, but something far more interesting. For about 200 years at a time, it enters a phase where its orbit appears to circle Earth when viewed from our perspective, earning it the nickname Earth's second moon. Then, just as mysteriously, it transitions back into its horseshoe pattern. The implications of this relationship stretch beyond celestial mechanics. Neutron belongs to a class of objects called co-orbital asteroids, which could hold clues about Earth's early history. Some scientists speculate these cosmic hitchhikers might have formed alongside our planet, while others suggest they're captured interlopers from the asteroid belt. What's certain is that Neutron won't be our dance partner forever. Simulations show its current orbital pattern only lasts another 5,000 years before gravitational nudges from other planets send it spiraling away. What's truly remarkable is how recently we discovered this intimate connection. For millennia, Neutron was just another speck of light moving against the stars, its secret rhythm hidden in plain sight. It makes you wonder what other cosmic companions might be lurking in Earth's gravitational shadow, waiting to reveal their stories. Deep within the Sun's core, conditions are so extreme they make the most volatile environments on Earth seem tame by comparison. At its heart, temperatures soar to a blistering 15 million degrees Celsius, hot enough to vaporize any known material instantly. But it's not just the heat that defies imagination. The pressure here is crushing, reaching 250 billion times the atmospheric pressure we experience at sea level. That's like stacking 30,000 Empire State Buildings on every square inch of your body, compressing hydrogen gas until it becomes as dense as solid gold. This unimaginable environment is where the magic, or rather, the physics happens. Under such extreme conditions, hydrogen atoms, which normally repel each other due to their positive charges, are forced so close together that they overcome their natural aversion and fuse. When 4 hydrogen nuclei collide with enough force, they merge into a single helium nucleus, releasing a burst of energy in the process. This transformation, known as nuclear fusion, is the Sun's powerhouse, generating the light and heat that sustain life on Earth. Every second, the Sun converts 600 million tons of hydrogen into 596 million tons of helium, with the missing 4 million tons transformed into pure energy, enough to power human civilization for 500,000 years. But here's what's even more mind-bending. The energy produced in the core doesn't immediately race toward the surface. Instead, it embarks on a slow, torturous journey. Photons, the particles of light created in these reactions, bounce around like pinballs in the dense plasma, colliding with atoms over and over. A single photon can take anywhere from 10,000 to 170,000 years just to travel from the core to the Sun's surface. Once it finally escapes, that sunlight reaches Earth in a mere 8 minutes. That means the warmth you feel on your skin today was forged in conditions so intense they predate human civilization by millennia. The core's density isn't just a curiosity, it's a delicate balancing act. If the pressure were slightly lower, fusion would sputter out and the Sun would collapse under its own gravity. If it were higher, the reactions would rage out of control, causing the Sun to burn through its fuel catastrophically fast. Instead, it maintains this perfect equilibrium, a self-regulating furnace that's been burning steadily for 4.5 billion years. What's equally fascinating is how we know any of this at all. Scientists can't probe the Sun's core directly, so they rely on sophisticated models and observations of solar vibrations, ripples on the Sun's surface that act like cosmic sonograms, revealing the structure and dynamics of its hidden heart. These studies confirm that the core is a realm beyond human experience, where matter behaves in ways that defy intuition, and the laws of physics are pushed to their limits. So the next time you bask in sunlight, remember, you're feeling the afterglow of a place where gold would float like styrofoam, where atoms are shattered and reborn, and where the very fabric of reality is rewritten every second. It's a reminder that the most ordinary things like a sunny day are fueled by processes so extraordinary they border on the surreal. Somewhere in the constellation Vulpecula, 63 light-years from Earth, there's a planet where the weather forecast reads like something from a nightmare. HD 1897 33b isn't just another hot Jupiter. This cobalt blue hellscape boasts winds that scream across its atmosphere at 8,700 kilometers per hour, carrying storms of molten glass that rain sideways with relentless fury. First discovered in 2005, this exoplanet orbits so close to its host star that a single year lasts just 2.2 Earth days. But proximity isn't the only thing turning this world into a cosmic furnace. Tidally locked with one face perpetually scorched and the other shrouded in darkness, the temperature difference between hemispheres creates atmospheric chaos. The dayside simmers at 930 degrees Celsius, hot enough to vaporize metals, while howling winds transport this superheated air to the nightside in a continuous planet-wide tempest. Now imagine standing on this world if you could. The cobalt hue comes not from oceans but from silicate particles in the atmosphere, the same material that forms glass. As these particles condense in the upper atmosphere, they coalesce into droplets of molten glass that get caught in those supersonic winds. The result: horizontal hailstorms of liquid glass moving at 7 times the speed of sound, scouring the planet's surface in an endless, abrasive downpour. What makes HD 1897-33b particularly fascinating is how we know about its horrors. Astronomers used the Hubble Space Telescope to analyze starlight filtering through its atmosphere, detecting not just the telltale blue tint, but the spectral signatures of vaporized silica. The planet's extreme conditions actually make it easier to study than calmer worlds. Its puffed-up atmosphere, bloated by the intense heat, allows more light to pass through, revealing its chemical secrets. But here's what really twists the knife. This glass rain might not even be the planet's most brutal feature. Some models suggest the winds are so powerful, they could strip the atmosphere from any rocky world unfortunate enough to orbit this closely. HD 1897-33b survives only because it's a gas giant, with enough mass to cling to its seething shroud of vaporized rock and metallic gases. This isn't just a planetary oddity, it's a window into how exotic weather operates across the cosmos. From diamond rains on Neptune to rubies and sapphires swirling in the clouds of gas giants, the universe proves that Earth's water cycle is just one pedestrian version of how matter can move and transform. HD 1897-33b takes that concept to its most violent extreme, where the very rocks themselves become fluid, caught in a perpetual storm of celestial glass blowing. What's haunting is realizing this isn't science fiction. Right now, as you watch this, that cobalt world is spinning in the darkness, its skies alive with superheated crystal shards moving faster than bullets, a reminder that the universe doesn't just cater to life as we know it. Somewhere out there, entire worlds exist where the weather itself is made of nightmares. The Milky Way isn't just floating peacefully through space, it's locked in a gravitational embrace with a cosmic neighbor that's pulling us closer every second. 4 billion years from now, our galaxy will collide head-on with the Andromeda Galaxy in one of the most spectacular mergers the universe has ever witnessed. Right now, Andromeda barrels toward us at 110 kilometers per second, covering the 2.5 million light-years between us with terrifying inevitability. When that fateful impact comes, it won't just reshape our galaxy, it will rewrite the night sky forever. Picture this: as the two spiral galaxies first begin to intertwine, their colossal gravity will warp and stretch their structures like taffy. Stars won't collide, the distances between them are too vast, but their orbits will be flung into chaos, painting swirling arcs of starlight across the heavens. For nearly 2 billion years, the two galaxies will perform a slow-motion dance, passing through each other multiple times before finally merging into a single, enormous elliptical galaxy astronomers have nicknamed Milky. The result will be a featureless, golden-hued blob of stars, a far cry from the Milky Way's elegant spiral arms. Here's what makes this collision so mind-bending. Despite the violence of the process, Earth, if it still exists, might barely notice. Our solar system will likely be hurled into the outer reaches of the new galaxy, but the chances of stars or planets colliding are almost zero. The real spectacle will be in the sky. As Andromeda approaches, it will grow from a faint smudge to a looming disk, eventually spanning half the night sky. When the galaxies merge, the combined light of 1 trillion stars will create a dazzling, continuous glow brighter than 1,000 full moons, turning night into perpetual twilight. What's wild is how we know this will happen. By measuring Andromeda's blue shift, the way its light compresses as it moves toward us, astronomers have confirmed the collision's inevitability. Computer simulations show the merger's precise choreography, revealing how gravity will twist both galaxies beyond recognition. Even more fascinating, this isn't unique. Galactic collisions are common in the universe. Hubble images reveal distant galaxies caught in similar embraces, their shapes distorted into surreal bridges and tidal tails. The aftermath will be strangely quiet. Without gas left to form new stars, both galaxies will have exhausted their fuel by then. Milky will glow with the fading light of aging stars, a monolithic tombstone marking the end of 2 cosmic eras. Yet, even in this distant future, the universe will keep turning. New galaxies will form, stars will ignite, and the cycle will continue, just without the Milky Way as we know it. So next time you gaze at Andromeda with binoculars, remember, you're looking at our galaxy's future partner in the slowest, most beautiful car crash imaginable, a dance of destruction set to a timer longer than life itself. Deep in the heart of the Perseus cluster, a supermassive black hole isn't just devouring matter. It's composing a symphony. In 2003, astronomers analyzing data from NASA's Chandra X-ray Observatory stumbled onto something extraordinary. Pressure waves rippling through the cluster's superheated gas, emanating from the black hole like cosmic ripples in a pond. These weren't ordinary waves, they were sound waves carrying a note 57 octaves below middle C, a frequency so deep it would take a piano with 7 extra octaves just to play it. Here's how this cosmic bass note works. As the black hole feasts on surrounding material, it doesn't consume everything. Some gas gets violently ejected in jets traveling near light speed. These jets slam into the surrounding galaxy cluster, creating shock waves that propagate through the million-degree plasma. The resulting sound waves are the equivalent of a B-flat, but at a frequency 1 million billion times lower than human hearing can detect. To put that in perspective, if this note were audible, its vibration would complete 1 cycle every 10 million years. But how do you hear a sound that old? Scientists took these impossibly slow pressure variations and did something ingenious. They scaled them up, speeding the waves by 57 octaves to bring them into the range of human hearing. What emerged wasn't a chaotic noise, but an eerie, resonant hum, like the deepest note from a galactic organ pipe. The recording, released by NASA, sounds unsettlingly melodic, a single tone hovering in the darkness, proof that even the most destructive forces in the universe can create strange beauty. What's fascinating isn't just the sound itself, but what it reveals about black holes. These cosmic titans aren't just silent voids, they're active shapers of their environments. The pressure waves from Perseus's black hole carry enough energy to heat the surrounding gas, preventing it from cooling and forming new stars. In essence, this low-frequency hum acts as a cosmic thermostat, regulating the growth of an entire galaxy cluster. The implications stretch beyond Perseus. Other galaxy clusters show similar pressure ripples, suggesting black hole singing might be universal. Some researchers even speculate these waves could explain why certain clusters are strangely hot at their edges, the cumulative effect of billions of years of deep space infrasound. Yet the most haunting thought is this: that note has been playing continuously for 2.5 billion years. Long before multicellular life existed on Earth, before the dinosaurs, before the continents took their current shapes, that B-flat was already echoing through the void, a cosmic lullaby from the depths of a black hole's hunger. It's a reminder that the universe doesn't just operate in light and gravity, but in sound too, a vibration so vast we had to shrink time itself to hear it. While most planets spin like tops as they orbit the Sun, Uranus performs a cosmic belly roll, tipped over at a jaw-dropping 98-degree angle. This ice giant orbits the Sun completely sideways, rolling along its orbital path like a celestial bowling ball. This extreme tilt isn't just a quirky feature, it transforms Uranus into a world of radical extremes, where sunlight lingers on a single hemisphere for 21 straight years before plunging it into an equally long, frigid night. Picture standing on Uranus during its summer solstice. The Sun wouldn't meander across the sky, it would spiral directly overhead in a tight circle, never dipping below the horizon, casting perpetual daylight over one pole while the other remains locked in darkness. As the seasons shift over decades, the Sun gradually sinks toward the equator, eventually rising and setting like it does on Earth until winter comes and the entire cycle reverses. This bizarre rhythm makes Uranus's climate unlike anything in our solar system. So what knocked this planet on its side? The leading theory involves a cataclysmic collision during the solar system's chaotic youth, a planet-sized impactor slamming into Uranus with enough force to send it spinning sideways, potentially even altering its rotation speed. Another possibility suggests gravitational tugs from ancient, since ejected sibling planets could have gradually torqued Uranus's axis over billions of years. Whatever the cause, the result is a world where the concept of up and down is meaningless. Its magnetic field is so lopsided, it doesn't even emerge near the geographic poles. The consequences of this tilt ripple through the planet's atmosphere. Unlike Earth's relatively uniform seasons, Uranus's prolonged exposure to sunlight creates bizarre weather patterns. When Voyager 2 flew past in 1986, Uranus was near its solstice, its south pole pointed almost directly at the Sun. Yet despite decades of continuous sunlight, the pole was colder than equatorial regions, defying expectations. Scientists now suspect the planet's interior heat distribution is as off-kilter as its rotation, with heat somehow trapped beneath layers of methane haze while the poles radiate energy into space. What's truly mind-bending is how this tilt affects Uranus's moons and rings. All 13 rings and 27 known moons orbit along the planet's tilted plane, creating a system that orbits the Sun like a giant wobbling bullseye. During equinox, when the Sun shines directly over Uranus's equator, the rings appear edge-on from Earth, a vanishing act that occurs only once every 42 years. Yet for all its oddities, Uranus holds clues about planetary formation. Its sideways spin hints at the violence of the early solar system, where collisions and gravitational chaos shaped worlds in ways we're still deciphering. It's a reminder that what we consider normal in our cosmic neighborhood might be the exception rather than the rule, and that somewhere out there, other tipped-over worlds might be rolling through the darkness, rewriting the rules of time and seasons. Imagine a bubble in space so vast you could fit 2,000 Milky Ways end to end across it, and inside almost nothing. This is the Boötes void, a spherical desert of cosmic proportions, stretching 330 million light-years wide with fewer than 60 galaxies scattered across its expanse. To put that in perspective, a region that size should contain around 2,000 galaxies based on the average density of the universe. Instead, it's a ghost town, a staggering emptiness that defies everything we know about how matter should be distributed. The mystery of the Boötes void, sometimes called the Great Nothing, was first spotted in 1981 when astronomer Robert Kirshner and his team noticed an unusual gap in galaxy surveys. At first, they thought it might be an error, a trick of incomplete data. But as telescopes sharpened their gaze, the void refused to fill in. Its scarcity of galaxies isn't just unusual, it's statistically improbable, like rolling a dice 1,000,000 times and never landing on a 6. So what carved this hole in the universe? One theory suggests it's the aftermath of a cosmic collision, not between galaxies, but between entire regions of space-time. In the early universe, vast bubbles of energy may have formed during the rapid expansion of the cosmos. Where these bubbles met, their walls could have created dense sheets of galaxies, leaving the interiors barren. Another idea posits that the void is a relic of a supervoid, a region where dark energy's repulsive force outpaced gravity, pushing matter away before galaxies could form. Yet the Boötes void isn't entirely empty. The few galaxies it does contain are oddballs, like isolated islands in an ocean of darkness. One of them, the dwarf galaxy NGC 5477, sits near the void's edge, its stars forming in eerie solitude. Astronomers call these void galaxies, and they're unlike their crowded cousins. With fewer galactic neighbors, they evolve in isolation, often retaining primitive, hydrogen-rich compositions, time capsules of the early universe's chemistry. What's haunting is the scale of this emptiness. If you were inside the Boötes void and looked up, the night sky would be nearly black, with only faint smudges of light from those rare galaxies breaking the darkness. It's a reminder that the universe isn't just full of wonders, it's also full of absences, gaps so vast they challenge our understanding of structure itself. And the Boötes void might not be alone. Other supervoids have been spotted, like the KBC void and the cold spot in the cosmic microwave background, each hinting at larger patterns we don't yet comprehend. These cosmic deserts force us to ask, are they flaws in the fabric of the universe or features? The answer might rewrite the story of how everything and nothing came to be. Here's something that will bend your sense of time literally. On the moon, clocks tick ever so slightly faster than they do on Earth. Thanks to Einstein's theory of relativity, the weaker gravity on our lunar neighbor means time itself flows differently there. Over the course of a single Earth day, a clock on the moon would gain about 56 microseconds compared to one back home. That might sound negligible, but for precision systems like GPS or spacecraft navigation, it adds up fast. That's why scientists are now proposing something revolutionary: Lunar Standard Time, a dedicated time zone for the moon. Think about it, the moon's gravity is just 1/6 of Earth's, which means its gravitational tug on spacetime isn't as strong. According to relativity, time runs slower in stronger gravitational fields. So while we're stuck in Earth's gravity well, watching seconds crawl by at their usual pace, an astronaut on the moon would be aging a tiny fraction faster. This isn't science fiction, it's measurable physics. Atomic clocks placed at different altitudes on Earth already show this effect. Clocks on mountaintops tick faster than those at sea level. On the moon, the difference is even more pronounced. But why does it matter? Imagine future lunar bases coordinating with Earth, satellites, or other spacecraft. A delay of even microseconds could throw off high-speed communications, robotic landings, or even synchronized experiments. Without a standardized lunar time, every mission would have to manually compensate for the drift, creating a chaotic patchwork of corrections. That's where Lunar Standard Time comes in. By establishing a unified reference, astronauts and machines could operate in sync without constant recalibration. The real challenge is deciding how to define it. Should lunar time stay tethered to Earth's clocks, adjusting periodically like leap seconds, or should it run freely, creating an entirely separate system? The European Space Agency has already begun developing frameworks for this, suggesting ultra-precise lunar atomic clocks that account for both relativity and the moon's unique environment. Here's the kicker: this isn't just about the moon. As we venture to Mars, where gravity is about 1/3 of Earth's, or even asteroids with negligible pull, each destination will need its own time standard. We're entering an era where time zones won't just span continents but entire worlds. So the next time you glance at the moon, remember, up there, seconds slip by a little quicker, and humanity is one step closer to synchronizing the cosmos. You might think space is completely empty, a vast nothingness stretching between stars and galaxies. But here's the reality. The cosmos is more like an impossibly thin soup, with a few stray atoms floating in every cubic meter. This near-perfect vacuum isn't quite perfect enough to call it truly empty. Picture a single grain of sand suspended in an Olympic-sized swimming pool. That's roughly the density of matter in interstellar space. What's actually out there? Mostly solitary hydrogen atoms, the universe's simplest and most abundant building blocks. These lone survivors drift through the void at hundreds of kilometers per second, leftovers from the Big Bang or cast-offs from dying stars. Occasionally, they collide so rarely that a single atom might travel for years before bumping into another. Yet this sparse population plays a crucial role. Over billions of years, gravity herds these atoms together into dense clouds, where they eventually ignite as new stars, the famous pillars of creation in the Eagle Nebula. Those towering columns are just particularly packed neighborhoods of this cosmic haze, with densities approaching millions of atoms per cubic centimeter, still a vacuum by earthly standards. Even more surprising, space also contains a sprinkling of heavier elements: oxygen, carbon, even traces of iron blasted into the void by supernovas. These microscopic particles form intricate dust grains, some with icy coatings of water or methane. When starlight hits them, they can align like compass needles, creating the polarized glow that guides astronomers studying magnetic fields across the galaxy. But the real shocker isn't what's there, it's how it moves. The solar system is currently plowing through a cloud of this interstellar medium at 25 kilometers per second, creating a bow shock in front of our heliosphere like a ship cutting through water. The Voyager probes, now in interstellar space, have detected the increased particle density firsthand, a tangible reminder that even the emptiest reaches of space still hold secrets. This near-nothingness has profound implications. It's the reason light travels so effortlessly across billions of light years, yet also why spacecraft can't rely on aerobraking like airplanes. It's why astronauts don't freeze instantly in shadow without air to conduct heat. Temperature changes happen agonizingly slow. And it's why the universe isn't pitch black. Those sparse atoms scatter just enough starlight to create a faint, uniform glow between galaxies. So next time someone calls space a vacuum, remember, it's the closest thing to nothing we've found, but it's still humming with whispers of atomic activity, a subtle backdrop against which all cosmic drama unfolds. At the outer edges of our observable universe, where galaxies fade into darkness, there's a radical idea reshaping how we understand reality itself: the holographic principle. This mind-bending theory suggests everything we perceive in three-dimension stars, planets, even our own bodies, might actually be a projection of information encoded on a distant, two-dimensional surface, like a cosmic DVD player projecting an illusion of depth onto the screen of existence. The roots of this idea trace back to black holes. In the 1970s, physicist Jacob Bekenstein discovered that the amount of information a black hole can contain isn't proportional to its volume, as you'd expect, but to its surface area, specifically the area of its event horizon. This odd finding hinted at something profound. All the data describing what's inside a black hole could be somehow stored on its boundary. Decades later, string theorists like Leonard Susskind and Gerard T. Hooft expanded this concept to the entire universe, proposing that our 3D reality might be similarly encoded on a vast, unseen 2D shell at the edge of everything. Think of it like a hologram on your credit card, a flat surface that creates the illusion of 3 dimensions when light hits it just right. In the cosmic version, the light is the fabric of space-time itself, vibrating in patterns that trick us into perceiving depth, solidity, and separation. Every particle, every force, every flutter of a butterfly's wing could be nothing more than fluctuations in this underlying code, playing out like pixels on the universe's ultimate display. What's wild is that this isn't just philosophical speculation, it has mathematical teeth. The equations of quantum gravity, when applied to the universe's boundary, perfectly reproduce the physics we observe in our 3D world. It's as if the universe is performing an unimaginably complex calculation, rendering reality in real time like a video game engine drawing a virtual landscape. Some versions of the theory even suggest the boundary isn't out there at the edge of space, but all around us, every surface, every screen, even your skin acting as a tiny fragment of this cosmic projector. The implications are staggering. If the holographic principle holds, it means the universe operates like a quantum computer, with every event predetermined by bits etched onto its outer shell. Free will, the passage of time, even the distinction between past and future could emerge from this deeper layer of information. It also solves one of physics' biggest headaches: how to reconcile Einstein's smooth spacetime with the jittery unpredictability of quantum mechanics. In a holographic universe, there are two sides of the same coin, like watching a movie versus reading its script. Critics argue the theory is untestable, but experiments are already probing its edges. Gravitational wave detectors might someday spot subtle noise in spacetime's fabric, the pixelation of reality at unimaginably small scales. Other teams are studying the cosmic microwave background for anomalies that could reveal the universe's underlying code. Even if the holographic principle isn't the final answer, it's a reminder that reality might be far stranger, far more layered than we ever dared imagine. So the next time you gaze at the night sky, consider this: every star, every galaxy, even the void between them, might be nothing more than a shimmering mirage, a grand illusion painted onto the canvas of the cosmos by forces we're only beginning to decipher. The universe isn't just vast, it could be the ultimate magic trick, hiding its deepest secrets in plain sight. From sideways glass rain on distant exoplanets to black holes singing bass notes across cosmic voids, our journey through space's strangest secrets has revealed just how bizarre reality can get. Think about it right now. The moon is inching away from us, Saturn's rings are collapsing into oblivion, and somewhere out there, a planet made of diamond orbits a carbon-rich star. Yet for every mind-bending fact we've uncovered, the universe taunts us with countless more mysteries. What dark energy is accelerating cosmic expansion? How did life emerge from stardust? Are we truly alone, or is some other civilization gazing at their night sky, equally awestruck by the unknown? These aren't just trivia, they're humbling reminders of how much we've yet to learn. The cosmos operates on scales and timelines that dwarf human experience, rewriting the rules of physics in ways we're only beginning to grasp. Even our most advanced telescopes capture less than 5% of the universe's contents. The rest is hidden in the shadows of dark matter and energy. Every discovery peels back a layer, only to reveal deeper questions beneath. So here's where you come in. Which fact left you speechless? Was it the neutron star spinning faster than a kitchen blender, or the alcohol cloud that could fuel eternity? Maybe the great red spot's slow demise or the holographic universe theory made your brain do backflips. Drop your favorites in the comments. We'll dive deeper into your top picks in future videos. And if you've got a space mystery keeping you up at night, shout it out. From quantum foam to quasars, there's always another cosmic rabbit hole waiting to be explored. Because the truth is, this isn't just a list of facts, it's an invitation. An invitation to stay curious, to question, and to remember that every time we look up, we're not just seeing stars. We're witnessing a story still being written, one staggering revelation at a time. So keep wondering, keep exploring, and above all, keep looking up. The universe has only begun to spill its secrets.